Hi folks, it's Mr. M here with another video. This time we're looking at function notation. So quite a few things here that we want to go over. Starting off with functions are used all throughout mathematics, so mathematicians came up with function notation to make it easier to work with them. So function notation can be used even when we don't know the details of a particular relationship, even when we don't know what the rule is or the process is, we can still make use of function notation to help describe what is happening or to just label the structure here. So really, what I want you to understand here is given by this this setup right here. So this is the key structure of a function. What I need you to know is that we're taking in an input. There is a, like as you can see in this blurb right here, I want you to understand that there's always a link between, for a function, there's always a link between the input and the output. And that link is a mathematical process. This is what the function is doing. Okay, so let's dissect this a little bit. We can give our function, we can denote it any letter we like. Let's just give it the letter F. And then X is the input value, or the independent variable here, the input. And then the f of x, this is read as f of x, so it's not f times x. This is just saying I have a function and I'm feeding it the input value x here. It denotes, so that whole thing, f of x, denotes the output of the function when the input is x. So in other words, f of x is equal to y, right? In the past, we've dealt with just y equals mx plus b, y equals ax squared plus bx plus c, those kinds of situations. But now we're defining, we're going into something that looks like a more of, we're expanding that now. So if we take a look here, I have, so I have my function right here. It's denoting the value output of a function when the input is x. In other words, f of x is equal to y. Good. So let's piece this, let's dissect this a little bit more here. I can see that here I have an example of a function. This is the process right here. This is the rule. And let's just start from the beginning. So I have my name, my f right here. That's the name of the function. I give it the letter f. It can be any generic letter I like, but sure, we'll go with f for function. Next, what we have here is the entire left side. So f of x, this is the output value of the, the output value of the function. In other words, it's like y, the dependent variable. X right here is the input value, or the input, the independent variable, x. And the right side here, this is the rule, the process. This is the link that joins, that tells me what is happening to my input. So here, if I were to describe this in words, I would say, well, my input is getting doubled, and then 1 is being added to it. That's how I get my output. Okay, good. Now that we understand that, one other thing to add to this list is not to confuse f of x with multiplication, okay? That's a very common misconception. We'll go through some misconceptions in a little bit, but it's very common in the beginning to think of this as f times x, but it has nothing to do with that. There's nothing to do with multiplication here. It's just a rule, a system for a convention for labeling rules and organizing our thoughts here, organizing our math here. So the entire symbol f of x represents a function, its input and its output. It's not the same as an algebraic expression. Yes, so it's not just f times x. So think of this as a machine, right? It's a function machine. We're feeding it x, we get f of x. Okay, and this could be our rule here, for example. All right, so let's take a look at evaluating some functions. Here, I have a function f of x. It takes in a value of x, it doubles it, and then adds 3 to it. That's f of x. I have another function g of x, which squares my x, my input, right? Whatever input I have, It squares it and then subtracts that input from that squared number. Okay, or that squared value. So here is an example, f of 6. Well, my input is 6. I'm plugging in that input into x. So all the x's I'm replacing with 6. So then f of 6 becomes, I double the 6 and I add 3, right? That's what I'm saying here. I double the input and add 3. My input is now 6. So when I evaluate this, it's just 2 times 6, which is 12, plus 3, which is 15. Okay. Here, for g of negative 5, well, now my function is no longer x, it's gf. I'm looking at the function g of x right here. G of x is a different rule. It's a different process. It's a different function. Here I'm squaring it and then subtracting the original, the input. So if my input just so happens to be negative 5, well, I'm going to square negative 5, not just the 5, also like the entire negative 5. That's why brackets are super important. We're going to talk about this a lot. And then I subtract from that the input, which is negative 5. So when I simplify this, I get 30. Here, my input is an actual expression, right? My input, that's the beauty of functions. I'm not limited to just value inputs. Now I can have expressions as inputs as well. So my input is now x plus 1. So I'm going to replace my input here and here and here with x plus 1. So I'm squaring x plus 1 and I'm subtracting the group x plus 1, right? That's just the rule for g of x, the function g. And now I simplify this. When I square x plus 1, I get x squared plus 2x plus 1. When I subtract x plus 1 from that, I get this, collecting like terms there, x squared plus x. Really, this right here, this next example is just showing you that in f of x or g of x, the x here is not, it doesn't always have to be x. It's just a placeholder, right? So it's just saying whatever that input is, I'm just doubling it and then adding 3 to it, to that result. If I'm dealing with the function x, that's the rule, that's the process. So let's say I'm plugging in a symbol here, which is a triangle. I'm going to double that triangle and then add 3. That's what the function does to that triangle, the input, which is the triangle. Okay. I hope you could see the pattern here. Like every time I'm having the function f, I'm just doubling the input, adding 3. I'm doubling the input, adding 3, right? When it's g of x, I'm squaring the input and then subtracting that input. I'm squaring the input and then subtracting that input. Okay, and then I just simplify. Okay, here's a g of 2x. I'm squaring the input, which is 2 of x, and subtracting that input. And I simplify. Okay, here I have something very interesting. I have a function inside a function. So this is called a composite function, or it's like nesting here. So I want to always start from the inside out, right? This way it's, it's cleaner and it makes sense logically as well. So really, I'm looking at f of negative 3 first. So I'm trying to figure out what, if my input is negative 3, what does my function do to that negative 3? Well, it doubles that negative 3, and then I add 3 to it, right? That's what this rule says. Okay, so I can simplify that. That just ends up being negative 3. Now I have a new input for my g function. So my g function is a different rule. It's saying I have to square that input and then subtract that input. Well, now the input for g is negative 3. So I square that negative 3, then I subtract that negative 3. All in all, I get 12. Okay, so very well. Moving on with this analogy, with these examples, here I have another example. I'm going to double the function output of, f of negative 1. Let's go ahead and, it's super helpful to write brackets, a lot of brackets when we're dealing with functions. So I want to kind of look at f of negative 1. I want to focus in on that. And that just means that I'm going to double my input. So double negative 1, add 3. And that result, what I get here, I'm going to double. So this simplifies, the inner brackets, negative 2 plus 3 is just 1. And then 1 times 2 is 2, right? So this just simplifies to 2. And then I'm looking at g of 3. Well, my g function is saying my input gets squared, and then I subtract x. My input, which is 3, is getting squared, and then I'm subtracting 3, which is the input, right? So now I simplify this, and I get 6. So at the end of the day, double of f of negative 1 plus g of 3 is equal to 8. Here I have something which is finding the g of f of x. Okay, so now the g f of x, well, I know that f of x, that rule is just doubling the x and adding 3, because it's just x here. That's the rule. And now I'm trying to find the g function for that input. So the g function tells me I square the input and then subtract that input. Here, I'm squaring the input, and subtracting that input. So wherever I saw an x in g of x, here, instead of x now, I have an expression 2x plus 3. So I'm replacing this and this with 2x plus 3. And then that's the rule. Then I simplify, and I get this. Okay. Here's an interesting case. So this is a situation where I'm trying to find x, and I give you the y value. So again, look back at the function rule. It's saying f of x is equal to 2x plus 3. Okay, well, I give you f of x. So now, start with this. F of x is equal to 2x plus 3. Replace f of x. I tell you the output. So the output is 10. What's the input? That's what the question is asking us. So let's just solve this equation now. You're going to subtract 3 from both sides and divide by 2, and you get the fraction 7 over 2. So when the input is 7 over 2, my function, which is this right here, will give me a y value, an output of 10. That's what that represents. So it's just always a relationship between input and output. It's a process. Find x if g of x is equal to 2. So here, g of x is 2, so I'm going to just replace g of x with 2, and then I'm going to solve for x. In this situation, I want to, it's a quadratic equation here, so I want to bring all the 2, so I want to subtract 2 from both sides, and I get something like this, and then I can factor this using the man method, 2 numbers that multiply -2 and add to -1. Well, those numbers are -2 and 1. And then I use the zero property rule to help me figure out that, well, if two things multiplied are equal to 0, well, then either this is 0 or this is 0. So then x minus 2 is 0 when x is 2, x plus 1 is 0 when x is -1. So those are my two solutions. Okay. Here is another model, right? These were all equations. We were evaluating functions from using equations and expressions. But here we have a graph, more visual definition of a function, right? Model depiction of a function. So here in this case, I'm looking at, well, I'm trying to figure out what is the output when my input is 2 on this graph. So my input is my x, right? So when the input is 2, well, the output is -2, just right here. So that is that. The input is -3, so -3 is input. Now, where does my graph cross the x equals -3? Or what is the y value? What is the output at x equals -3? Well, it's just 4. So right here. So that's why it's 4. The output is 4 when the input is -3. If x is equal, so let's find x. If f of x is equal to 2, that means now I give you the output. I tell you it's 2, and find what the input is. So -2. Okay, here I'm telling you the output is 0. So literally the output is 0. Find the input. So literally, where does it cross the x-axis? Y equals 0 is, or the f of x equals 0 is just the x-axis. So here I have one solution, so x is equal to -1, and I have another solution, x is equal to 5. Let's take a look at ordered pairs here. We could see. So here, this is my function f of x. It's a list of ordered pairs here, and then this g of x, a list of ordered pairs, okay? So g of 5. So I'm looking at when my input is 5 in the g function, what is my output? Remember, for functions and ordered pairs, it always goes x, y. So input, output, right? So if g is f, when the input is 5, my output is 8 for the g function. So this would be 8. For the f function, when my input is 2, my output is 5. So it's 5. Now this one is like the nesting again. It's the composite function. So I'm looking at g of -2 first. I'm looking at what is the output of g, of the g function. What does it produce when an input of -2 is fed in? Well, an input of -2 in the g function gives me an output of -3. So I'm actually just trying to find f of -3. In other words, g of -2 is equal to -3. Now I'm looking at f of -3. So I'm looking at my f function. When the input is -3, the output is 5. So it's just 5. Okay. Lastly, we look at an application here. So we have a car company that rents cars for $50 per day plus $0.15 per kilometer, so or 15 cents a kilometer. This is an example of a linear relationship or a linear function because we have a fixed cost, $50 per day, and we have a unit rate or unit cost, which is, the more the distance goes higher it travels, the more the cost goes up that way. So we want to express the daily rental cost C, so we're giving the name C for the function, C as a function of the number of kilometers D traveled. So we're trying to figure out what is a cost function, cost as a function of distance, right? And we could say C of D is equal to the original, like the starting 50, plus 0.15D. Okay, so that's the cost function. So for any distance, I can figure out the cost by using this rule right there. For any input, I can figure out the output. Now I want to determine the rental cost if I drive 472 kilometers. So my D, that's my input right here. So I'm trying to figure out C of 472. Now I just replace that 472 into my system right here, which is I add 50, I take 50, add it to 0.015, 0.15, and multiply that by the D value or the input, which is 472. So when I simplify that, I get 120.8 or $120.80. Here, it's like the opposite. I'm trying to figure out how far I can drive in a day for $80. This is a cost, right? $80, let's say that's how much money I have. Then now my C of D is going to be 80. And now I'm trying to figure out, solve for D. So I could do the math here, or the input. I could do the math here and figure out that my input is going to be 200 kilometers, or that's how much I can drive with $80. Now the last question here is C of D a function? Well, actually it is a function because for each distance, D, which is my input, there is exactly one total cost C of D, or the output. In other words, it's linear and it's not like a vertical line, so it is a function. Each distance has one and only one cost. So hence it is a function. Okay, this right here is the homework. Actually, just before jumping into the homework, I actually went ahead and just for you folks, I used ChatGPT here strategically because I asked it, what are the most common misconceptions that students make when they're first learning about functions, right? Because I can understand that it can be a little bit ambiguous. So here's what it gave me, right? It's common mistake, and then quick language fix, what to say, and then a mini example here. So let's just go through this pretty quick. Okay, so misconception number one, and you may be having this misconception, so hopefully this will clear it up. Thinking that f of x means f times x. So f bracket x is read out loud as f of x. It means the output when the input is x. Yeah, it literally means my input is x and f of x tells me once I apply the rule, it's the output. So here is an example. If f of x is equal to 2x plus 1, then f of 3 is literally saying, the function here is saying I double my input and add 1. So I doubled my input 3 and I added 1 to get 7. So now it has nothing to do with f times 3. It's not 3f or anything like that. It literally is 7. F of 3 is 7. Okay. Number 2, confusing input x with output f of x. So yes, x is the input, it goes in, and f of x is what comes out. F of x is the output, right? So let's say here, this is probably you're missing the process here if you're making this misconception, right? So the input 3, let's say there's a rule, a process, which is saying double that input 3 and add 1. So now when I double 3, I get 6, and then when I add 1, I get an output of 7. So I say x is, when my input is 3, f of 3, or f of x when x equals 3, is 7. Okay. Substituting without brackets, especially negatives, this is a big one. A lot of us make these mistakes in the beginning. So when we plug in a value, we want to replace every x with that value in brackets. This is critical, absolutely very good to note. So if f of x, if my function is saying, well, I have an input, it's saying, if the rule is saying square that input and subtract 5 times the input, and then let's say my input is -2, well, I want to make sure that the whole -2 gets squared. Not just the 2, not just the negative, but the entire input gets squared. And then I have to subtract 5 times the input. So there's lots of negatives here. First of all, -2 times -2 is +4. And then -5 times -2 is +10. So this ends up being +14. Right? If you didn't include brackets here, you wouldn't get that answer. And it has to be precisely this answer. So f of -2 for this rule right here is 14. Okay. Number 4, thinking that the input must literally be x. That's true. I know we always say f of x, but the letter x is just a placeholder. It's the input. It's a placeholder. You could replace that with a question mark or a mystery box. It could be anything. Any input symbol works. We just like to use x because it's like consistent with what input is, independent. As opposed to like y, which is dependent, right? The dependent variable. So we use x here. So if f of x is equal to x squared, then f of t is t squared, right? And f of 3 is 9, right? If it's a different variable, it stays as an expression. If it is a number, it can be evaluated to give me a value. And then here, I can have expressions here. If the input is x plus 1, well, right, we started here with the original rule. That's what I was given. Then my rule tells me just square that input. So I just squared that input. If the input is t, I just squared that. If the input is 3, I just squared that. That's the rule. It's going from input to output. Okay. All right. Number 5, mixing up evaluating versus solving. Yeah, this also comes up a lot. Evaluate means plug in an input. Solve means find the input that gives an output. So we saw that before, right? Evaluate, this example, so here, f of x is equal to 2x plus 7. When we evaluate, we're doing something like this. F of 5, when we evaluate that, my input is 5. I'm going to double that input and add 7. And so double of 5 is 10 plus 7 is 17. So I just evaluated there. But I'm doing something like solving when I give you an output. Let's say f of x is equal to 17. So now you're going to use the rule double x plus 7 is equal to 17, and you're trying to figure out what x is now. So you're going to subtract 7 from both sides and divide by 2 here to get x equals 5. So that's, solving versus evaluating. Here, treating f of 2 equals 7 as a point. Yeah, this is not really a point. F of 2 is equal to 7. The point, the 7 is the y value, right? And the point here is input, that's my x value, output, that's the y value. So the point really is 2, 7. From the rule or graph, if f of 2 is equal to 7, then the point on the graph is 2, 7, right? You gotta use like coordinates here. Okay. Lastly here, we have one last misconception. Ignoring domain restrictions, assuming every input works. We'll talk more about this in a future video, but here it's just looking at before evaluating, you want to ask, is that input allowed, right? Let's say my function h of x, why not, is equal to square root of like x minus 5. Then h, when the input is 2, doesn't make sense because it wouldn't be real, right? I can't, my input minus 5, if I put an input of 2, 2 minus 5 is a negative number. I can't take the square root of a negative number. It won't be real anymore. So then that wouldn't make sense. So I would want to restrict the domain there. We'll do more of this later, but if g of x is equal to 1 over x minus 4, then clearly x cannot be equal to 4 because then the denominator would be equal to 0. 4 minus 4 is 0. 1, like any number, can't be divided by 0. It just wouldn't, it would be undefined. So really, folks, that is like a lot there, I know, but it is a helpful summary, I think, to help you look at, learning function notation for the first time. This is the homework for this section from the Functions 11 textbook. Go ahead and give that a go. Thank you and have a great day.